Buhov did his master's degree at the University of Macedonia. He's an expert on ICT and mobile security. And today he's going to talk about defending modern Android apps with TLS certificate pinning and notary services. Damjan, the stage is yours.
Thank you for the introduction. So, welcome to my talk. So, observed from the user's perspective, security was not a hot topic before in the past. However, there was a turning point, which was basically the Snowden's revelation, which revealed a lot of governmental programs that are still operating and running and collecting different kinds of user information. So this brings me to a conclusion, because smartphones became a part of our daily routines. So before I start presenting, I would like to ask you a question. Have you ever thought about the fact that the apps that you're using in your phone might not provide the security that they are supposed to provide? I was expecting that answer, so let's start with a small example. Is my communication actually secure? So on the left side we have a phone with some app, and on the right side we have a server. So how the communication should be performed? Usually the application, which I will refer to it during this presentation as a client, communicates with the server and exchange information. However, there is a possibility of an attack, a very common attack scheme present within these network communications, which is man-in-the-middle attack, where a third-party attacker is able to intercept each and every piece of information that we exchange with the server. That way, you can imagine what the consequences would be if you were about to log in your banking account throughout your banking application. So how do we know actually that our communication is secure? It's very easy when it comes to the browsers in Android, because all of them have this green lock that you see, and if you click on it, you will get an information about how secure the connection is the certificate valid, and so on and so on. But this is just the browser. What can we say about every other app? In my experience until now, I haven't seen any other app that has even a small indication that lets the users to know that they are communicating over a secure channel. So if we scale up a bit this problem, we have 2 billion smartphones and we have 2.2 million apps currently on the Google App Store. This number of 2.2 million applications is not static, and it is rising as I'm talking right now. So it's scaling very fast. Of course, that applications have to meet some criteria before they get published, in terms of not containing any malicious activities, and so on and so on. But what's even more important is that they process a lot of sensitive user information. A lot of the application, actually, the business services, are rapidly transforming to meet the needs of the mobile domain. So this means that we really now process sensitive information which is intended to stay secret in the first place. So we're going to tackle this problem from the user's perspective. And with that being said, the users have this fancy user interface, very nice design, but nobody actually knows what's happening in the background. What is the application doing? So the application might present some not so obvious threats for the users, because some of us are here very techy users, but let's take an example as an ordinary user who does not have any technical background. Everything what we can say for such users is that they, and also we as the tech users, we just rely on developers' capability and knowledge. So we cannot actually do anything. We just download the application, install it, and then from that point on the application runs through some patterns which only the developer is aware of. With such a drastic increase in the numbers of the application, it's natural to notice that the network utilization has changed drastically. So what we're aiming here is secure transfer of sensitive personal data. How is this achieved? This is achieved by use of some protocols, in this case SSL and TLS protocols. And what's even more interesting in Android, there is a freedom that developers are able to make their own custom implementation. However, as I will get back to it later in the presentation, there are a lot of problems with this approach. For example, back in 2012, a group of researchers tested more than 13,000 applications and found that more than 1,000 had completely broken implementation of the TLS protocol, which means that every single connection can be intercepted and every information transmitted can be very easily intercepted by an adversary. My personal opinion is that there is a lack of centralized body that will control the implementation of some crucial security mechanism. I will compare this with the Google Bouncer, for example, because Google Bouncer is actually a decentralized body that checks and proves that applications are benign before they are actually published to the market. So if there is some other centralized entity that would check specifically for the network configuration of the applications, we wouldn't have such problems. So just a brief introduction about the TLS Connection Setup. It's a handshake protocol, as most of you are aware. It's consisted of 4 phases, but we're interested only in phase 2. Why? Because this is the phase actually where the certificate sends, the server sends the certificate to the client, and the client uses certain information pre-shipped with its device to validate this certificate. How are these certificates validated? It's very straightforward and very simple, actually. It should be checked whether it's signed by a trusted certificate authority, the date of expiration, whether it has been revoked, and whether the host name matches the field of the subject alt name or the common name. It seems very easy, and indeed it is easy. However, we'll get back to it later and we'll see the results from our testing. So how is SSL and TLS protocols within Android apps? Basically, this is the most common protection mechanism that is used. So developers use these protocols to bind the app with the legitimate server. So that way they can establish secure communication and the users will be safe when transmitting data which is intended to be secure in the first place. We have more than 150 trusted certificates which are pre-shipped with the devices, but the question here is, by whom are these certificates trusted? Who is trusting those certificates? Actually, the answer is very simple, because Android has its default HTTPS API, and it implements a proper certificate validation. But there is another problem here which arises, that this puts an obligation to the developers that they have to acquire a valid certificate issued from some of those trusted certificate authorities. In the past, this was a problem, but nowadays there are a lot of services that offer free certificates just for use. The users should just sign up and they will get the certificate. So at this point, you might be asking yourself, okay, what would be the problem then? Actually, there are 2 main problems. The first one is the central role of the certificate authorities, which means that certificate authorities are central entities that they can issue and sign certificate for any address. This is actually one of the points, because all those certificates that are pre-shipped within the modern operating systems, such as Android and so on, are actually issued by these trusted certificate authorities. But what if some of these certificate authorities gets compromised? We had a case such as Komodo, DigiNotar, etc., etc. Or what if a CA issues a fake certificate for security, which was some very recent case with WoSign and GitHub? And even the latest thing, what would happen if the whole trust store is manipulated? And those certificates get in the hands of the adversaries. So as we can see, these are all parts of the news where we had a tons of problems with actually the trusted certificate authorities. So what would be the outcome of all this? Completely broken TLS implementation, which just provides enormous surface for man-in-the-middle attacks. The second problem is the custom handling of the certificates. There are certain cases where the user have to implement their own logic for the certificate validation schemes. Usually it is because they opt in to use self-signed certificates, and those certificates are not known to these trusted certificate authorities, so they are obligated to put their own validation checks, which would check for all those details previously mentioned. However, not all use self-signed certificates. Some of the developers just want to implement additional security features, such as certificate pinning, which is a technique that limits the use of particular certificates for this particular communication. However, if you notice the custom logic in the first bullet point, it's not actually a custom logic, because we've had cases where I personally found copied codes from popular forums, tech forums, directly into the app. So basically the developers, most of them, I'm not saying all of them, but most of the developers are putting no attention to security, so they just go, face a problem, address this problem to the forums, get an answer. If the answer works, it doesn't matter. From this point on, it is solved. This would lead to the broken implementation of the TLS protocol, which is a very common problem, as you will see in the following slides. It has been identified that main cause of this is lack of knowledge. Some group of researchers actually contacted the developers of some applications that were found to contain broken implementation and were asked about TLS and SSL, upon which they answered that they don't know what was that for. They just wanted to eliminate the error that they got testing the applications. But let's put the developers aside. We want to focus on the users now. And for the users, it's not easy to detect this flaw. We won't notice anything because the application will run, we will transmit our data, somebody might intercept it, we won't have any idea. In Android, we have Android permissions, which mean that every application should explicitly state what the application will use. But the problem is, for this, we have only the internet permission. So we have, okay, this application is using internet, but we need maybe a fine-grained permission system where it would say, okay, this application uses secure communication, at least still inform the user. This is not a proof that something will be changed, but as a notification. And last is the update interval, until a vulnerability is discovered, and the time until it gets patched. It renders the application completely unusable from a security point of view. So to prove our point, we performed an indicative experiment on 50,000 applications, 25,000 from Q4 in 2013 and 25,000 from Q4 in 2014. So we did not track any evolution of the application. This was just pure focusing on the custom implementation of the trust manager, because the trust manager is the one handling the TLS implementation of the TLS protocol. We used the maladroit script, and the results are the following. As you can see, for the applications from 2013, we have 17% with the blue. It's a completely broken trust manager. So a bit of clarification. If the trust manager is broken, everything's broken. What the categories is, it's either broken or possibly broken. This means that when it's possibly broken, it needs manual inspection. It might not be per se broken, but there are some errors within the implementation. But let's focus now just on the trust manager where it is completely broken. So we have 17% of the application no implementation, let's put it like that. If you go to the apps from 2014, which was rather staggering for me, we have the increase of 6%. And not just there, we have increase everywhere. So instead, improvement of this situation, it actually got worse. So, how can we fix this problem? Well, basically, I'm going to present now our tool that we developed. It's a combination of dynamic instrumentation techniques and certificate pinning. Our aim here is to protect the users against developers' errors into these certificate handlings. So we want to basically bring the control back to the users. What's really important to state here is that we did not perform any modification to the application files itself. This is pure on the system level, because it works at runtime and we're dynamically patching all of the applications. User is just alerted in the worst case scenario where we cannot really identify where this certificate comes from. So the current solution, tons of them about certificate pinning, but how we differ from them is that our proof of concept is basically device-based. So all of the certificate pinning was intended as a technique that would limit the use of certificates for particular application. We managed to shift this approach to a device-based solution where we can install our tool and basically enable the certificate pinning for all of the installed applications within. What's even more interesting is that our tool can be integrated in the Android OS system as a default setting later on. If Google or Sanogan decides to use it, it's perfectly fine to be integrated, and it can be integrated. Apart from certificate pinning, we are also using the TLS Notary Services, which are basically servers that monitor certificates, and they work on the principle of multipath probing. So basically, when we get a certificate that we don't know, we just send this certificate to the notary service, and then we just ask that, do we see the same certificate? Have you seen the same, or there are some changes? The actual implementation of the tool is based on CDS substrate. I don't know how familiar are you with CDS substrate. It's actually formerly known as mobile substrate, which is available for iOS also. It's a framework for dynamic instrumentation, which serves as a base upon which the users or the developers can develop their own modifications. You might have seen some examples. It has been vastly used in modifications of the GUI and effects on the screen and so on. However, we decided to use CDS substrate for a bit more important reason here. Because it's very deep in the system, we need an Android device with a root access, and of course we need knowledge for the instrumenting part. So what we do, actually, the code is consisted of just two classes, hooking class and custom trust manager class. The hooking class actually intercepts every HTTPS request and forces the application to use our implementation of the TLS protocol. If we take a look at this famous architecture of Android, when we take the bottom-up approach, we will see that we are in the Android runtime. The Android runtime is actually consisted of core libraries and the Dalvik virtual machine. So how Android works is basically every application is executed in its own space. This space is actually the Dalvik virtual machine. So when a new application is executed, a new virtual machine is formed. But since we are already within the runtime, our tool is actually included into this fork of a new Dalvik virtual machine. That's how we can intercept all of the system calls, but we are targeting just the HTTPS requests. So just briefly, I can show you now how this actually works. So we initiate a connection to a server, and then the server sends the certificate to the application. Because we have pins of certificates stored locally, we first check whether this certificate is already pinned, or if we are familiar with this certificate. And if we get a positive answer, then the connection is established and everything works just fine. In the case where we haven't seen this certificate before, we initiate a connection to the IT-SeCX certificate notary and send this certificate. Basically, this is the part where we ask the notary services, do we see the same certificate? Have you seen this certificate? Is it valid? The notary queries up and can return us two possible answers. I've seen this certificate, or I haven't seen this certificate. Depending on the answer, if we get a positive answer from the notary, the connection is established and everything is working as intended in the first place. But if we get a negative answer from the notary, then we terminate the connection and the user gets exactly such notification, which is this is basically a screenshot from the tool where we manipulated the certificate. So we do not allow connection to proceed if there is a certificate mismatch. This of course can reduce the usability of the application, but compared with the risks of what could happen if we allow this connection to be established, I believe it's a good trade-off. However, there are good news on the horizon. With Android 10, there is a whole new approach of certificate handling. So basically all the headaches that the developers had previously will go away, because there is just one config file now which has to be included within the application. This config file should contain the certificates that this current application should be used to validate against the server. So the whole idea of coding custom validation schemes goes away, which is a great thing for the developers. But do we have happy users in the end after all? We don't know, because first, again, the users will assign those certificates that will be used for the applications, but when the certificates expire, are the developers so consistent to update the application on time? Because this way, there is no room for a man-in-the-middle attack. If the certificate does not match, the connection is dropped by Google itself. So usability is reduced to minimum. What's interesting for us is that since we have the ability to hook system resources, we can easily hook this file and update the certificate with our checks for the developer. So basically there is also an advantage of our tool even with the newest Android upgrade. What's even more interesting is that according to the posts, what will happen with the previous operating system versions? Because all of this will take effect from the API version 24. So does this mean that the developers should have two versions of the application? One for Android N and one for the previous versions? If so, then we still have the problem that has been discussed throughout the whole presentation. To conclude, we basically developed a tool that enables dynamic patching of the TLS issue within Android apps. We shifted the whole strategy to work with all of the applications, not just single applications, and what was our intention in the first place, we brought the control back to the users. So now the users can know what their application is really using. Is it secure or not? At this point, I would like to thank you for your attention, and I'm open to questions.
Thank you very much, Damjan. Are there any questions?
how can I check that I can trust the notary, or how can the notary securely check that the certificates are really for the server I want to connect to?
Basically, if it's a public, and so this is, I can refer you also to some papers that are developed for just particularly for the notaries. But I believe that even if we take this case, the risk of the notary giving us a false answer is rather lower than allowing something that is broken in the first place. So the notaries is consisted of a lot of servers which monitor certificates. So basically, when we see a certificate, we get also additional information. When was this certificate first time seen? How many times was seen? And so on and so on. So it's not just pure binary information whether, okay, I know this certificate because it matters whether the notary knows the certificate from yesterday or it has been in the wild for some time.
But from a user perspective, it's similar to the situations that now I must trust the 150 root certificates that I get from Google,
Yes.
or I have to trust the notary. It's not,
Yes,
not
yes,
really much difference.
There is a big difference actually, because
the implementation of the protocol, of course.
the difference is the following, because if a trusted certificate authority gets compromised, and this trusted certificate authority has, for example, let's assume 100 certificates, then we have a very big surface that's upon which we can perform man-in-the-middle attacks. And when we are using the notary, we're limiting to the leaf certificates. So specifically for our tool, we're limiting the attack surface to minimum. So basically, if the notary lies us for some reason, it lies us only for one certificate, not for 100 certificates that might be issued from some trusted certificate authority.
Okay.
Further questions?
So your app needs root access, obviously.
Yes.
So probably not even wise for the non-tech-savvy users. And then the question remains, why should I trust you and give your app root access to my device? Does it really better the situation for me?
So, first of all, nobody should trust me because the code is publicly released, so everyone can go through the code. The intention of this is not to force you to install the application. I'm just showing a prototype that can be implemented in future versions of the operating system. I'm just showing that there is a way how to solve this problem, not by forcing the users, rather than giving an option that might be taken or might not be taken into considerations, and the whole process to be translated into a click of a button for the users, for example, as it is allow unknown sources for installation of third-party applications. This could be exactly the same feature, so allow custom implementation of the TLS protocol, which would be on or off. Because every operating system has its root access for some system things in the background. So.
Okay, so Cydia is already outdated since Android runtime, so Android 5. So your tool is now unusable, kind of, except for people running old Android, isn't it?
I would say that...
Like, you can't install Cydia, and your thing is depending on it.
That's true. However, if you check, I checked recently, actually yesterday, that I believe that 2/3 of the devices are still running the older versions of Android. So,
yeah, but
it's usable.
Too. And the other thing against using the system SSL provider is that if I would write malware monitoring all secured communications, also using Cydia, I would use the system one and not the specific custom ones, because I don't know them and I can't handle all the custom SSL implementations.
Yes, but I think we're on the wrong track here, because I'm not targeting malware. I'm targeting applications which are publicly available at the Google Play Store. So for malware, there is additional completely different topic where we can probably adapt our tool to be able to react appropriately to the malware that might be found.
Okay, thank you very much. We're out of time. Thank you for your talk.